Acha. Now what we're going to study about is the dispersion of light. Dispersion of light. Acha. Before studying about the phenomenon of dispersion, let us study something about light. There's some properties of light. Acha. The white light that you see from the sun, okay, is actually made up of combination of light. That means suppose this is the sun. Suppose this is the sun. Okay. The sun rose the sun throws at us all the combination of light. Okay. That means whenever we receive some rays from the sun, that ray is combined of multiple number of or multiple types of light. Okay. Such as gamma rays, X rays, okay, then violet rays, indigo rays, blue rays, red rays. And there are other type of rays also, infrared rays, then ultraviolet rays, sorry, infrared rays and radio waves. Radio waves. Okay. So the sun throws at us a combination of all these waves, a combination of all these light rays. Now, how do we differentiate? Suppose what we are receiving from the sun is nothing but a white light, okay, or a white type of light that we receive. Okay, the sunlight is nothing but white to us in nature. But how do I differentiate between gamma rays and X rays and violet rays and indigo rays? We use something called frequency of wave and wavelength of the wave. That means to differentiate between gamma rays and X rays, every type of ray, suppose gamma rays has a specific wavelength and a specific frequency. So for gamma rays, no, for every type of rays, for every type of rays, there is a specific wavelength, there is a specific wavelength termed as lambda and specific frequency mu of the wave of the wave. That means gamma rays has a specific wavelength and a specific frequency. X rays has a specific wavelength and a specific frequency. Similarly, these violet rays, indigo rays, blue rays, green rays, all these rays have a distinct wavelength and distinct frequency and distinct corresponding frequency. Okay, the relation between wavelength and frequency is nothing but wavelength into frequency is nothing but the speed of light. C is the speed of light. Okay. Okay. Now see, the speed of light of all these rays are same. That means all the light rays travel with the same velocity, the velocity of 3 into 10 to the power 8 meter per second. Now you are concerned about this specific spectrum of rays or this specific 7 types of rays. These specific 7 types of rays are called visible rays. Visible rays. So when you combine these 7 types of rays, they perform or they exhibit a color of white. Okay, so if you compile these 7 rays and put it together, they'll appear white to your eyes. Okay, And one more thing, okay, out here, out here, the speed of all the rays are same. The speed of, see the speed of light, no? The speed of all these rays are same. How are they different from each other? The lambda and frequency varies. That means lambda and frequency or wavelength and frequency of gamma rays is different from wavelength and frequency of X rays. Okay, so this is the property of light we must know before we start to understand the property of dispersion. Okay, so this is called visible rays which which appear white in color, white in color. That means a combination of these 7 rays appears white in color. Okay. Acha. Now we have a person called Cauchy. Okay. So start with Cauchy's equation to understand dispersion of light. Cauchy's equation. Okay. So before understanding Cauchy's equation, let us see a phenomenon. Okay. Suppose there is a prism. Okay. Suppose I pass a ray of light, a white ray of light or white light. White light. Okay, what is white light? White light is nothing but a mixture of those 7 visible light. Okay, white light is made up of violet, indigo, blue, green, yellow, orange and red. So white light is made up of combination of these 7 different light. So what happens when this white light goes through a prism is the white light gets separated into 7 different light rays. Okay, so while passing through prism, this white light gets separated into 7 different light rays. Okay, with violet at the bottom and red at the top, and in between are indigo, orange, yellow. Okay, V I B G Y O R. So it happens in the spectrum of V I B G Y O R. Okay, that means if a screen is out here, if a screen is kept out here, okay, if a white screen is kept out here, what happens is the violet color appears to be out here and the red color appears to be out here. Okay, the red color appears to be out here. So my question is, the refractive index or the refractive index of the prism was mu. Okay, so why did this white light, okay, get separated into 7 different colors? Okay, this is the concept of monochromatic light or polychromatic light. Monochromatic light means light containing only one. So monochromatic light means light containing only one type of wavelength. That means light that has only red wavelength or red ray of light or violet ray of light or blue ray of light. But that ray of light has only one wavelength, and those type of rays are called monochromatic rays. Polychromatic rays such as white light is a mixture of different rays of light. Okay, and what the Cauchy equation says is that although, okay, for a glass, suppose this prism was made up of a glass, although for glass the refractive index of glass is mu, the refractive index also depends upon the wavelength of the light. Okay, so refractive index depends upon the material of the medium in which the light is traveling, but refractive index also depends upon the wavelength of the light which is being refracted. So refractive index was a function of or was dependent on material of the medium, material of medium. Now till now we have studied mu sin I or mu I sin I is equals to mu R sin R. That was the property of refractive index of material of the medium. It also depends upon the wavelength of the light. Wavelength of the light. Okay. Now what the Cauchy equation says is that refractive index for a certain wavelength is equals to some constant a plus other constant b by lambda square plus another constant c by lambda 4 plus another constant d by lambda 6, and it goes up to infinity. Okay, out here this is nothing but Cauchy's equation. Okay, what this Cauchy says is that for the same glass, okay, for the same glass which is supposed to have same refractive index, okay, if I change the wavelength of the light, the refractive index of the glass changes. So up till now whatever questions you have done, see in all those questions they have been mentioned a monochromatic ray of light. Monochromatic ray of light means the ray of light has only one type of wavelength. Okay, and even if it was not mentioned in the question, it is usually assumed that whenever you are considering nu or whenever you are considering Snell's law, okay, we are dealing with monochromatic ray of light. Okay, and out here what happens for polychromatic light, the wavelength of violet color is different from wavelength of red color, and violet color deviates more than red color. Okay, now if we solve this equation, we get that, or from common sense we get that for the same material, wavelength of violet color, sorry, or refractive index of violet color, refractive index of violet color is greater than refractive index of indigo, is greater than refractive index of blue, is greater than refractive index of green, is greater than refractive index of yellow, is greater than refractive index of orange, is greater than refractive index of red. Okay, now just remember the angle of deviation for a thin prism. What is the angle of deviation for a thin prism? D is equals to A into mu minus 1. This was the angle of deviation for a thin prism, no? Where D was the deviation, A is the nothing but the prism angle, and mu is nothing but the refractive index. So by this equation, can I say refractive index of violet is more than refractive index of red? So can I, from this formula, can I say deviation of violet is much more than deviation of red? Okay, or by the angle by which the violet light bends or violet light bends is much more compared to the angle by which the red light bends. Okay, so out here by this equation I can simply say that deviation of violet light is greater than deviation of indigo, is greater than deviation of blue, is greater than deviation of green, is greater than deviation of red, is greater than deviation of orange, is greater than deviation of red. Okay, deviation of yellow, this one is yellow, violet, indigo, blue, green, yellow, orange, red. Okay, and this phenomenon where a polychromatic ray of light, polychromatic means mixture of different rays of light, gets broken down into its component, okay, due to the change in refractive index because of the wavelength of the light, is called dispersion of light. Acha. So the definition of dispersion of light, what is the definition of dispersion of light? Dispersion of light, just write down. Okay, when a polychromatic ray of light, when a polychromatic ray of light, what is polychromatic ray of light? A light ray which is made up of combination of light of different wavelengths. Okay, multiple number of light or multiple number of lights of different wavelengths combined to form a single polychromatic light. Refracts through a medium, refracts through a transparent medium, transparent medium. The ray of light, the ray of light gets separated into its individual light rays of their respective wavelength and frequency, wavelength okay, represented by lambda, and frequency. Okay. Now this splitting up of light rays is called dispersion of light. This phenomenon of splitting up of light rays, this phenomenon of splitting up of light rays is called dispersion of light. Is called dispersion of light. Okay. Now what we are going to study about is the dispersion of light rays through prism. Dispersion of light rays through prism. Okay. Now suppose there is a prism. If I send a white light, okay, white light out here, the white light gets broken into its respective component. Okay, this is violet light, this is yellow, this is blue. Okay, suppose violet, yellow, blue, and indigo all are in between. Okay, now the thing I'm concerned about is I must numerically define this dispersion of light, and in order to numerically define this dispersion of light for a prism, what I must study is I must study the dispersive power of a prism. Dispersive power of a prism. Okay, this is my scope of study. So now I'm trying to study about dispersive power of a prism. So in order to study about dispersive power, the first thing you must learn is what is the angle of deviation for violet rays. Okay, suppose this was the violet rays, this was the visible white light. Okay, this is the violet rays. Okay, so if the ray of light was undeviated, this is the angle of deviation of violet rays, or this is the angle of deviation of violet rays. And how is angle of deviation of violet rays given? Is equals to A into, or prism angle A into refractive index of violet minus 1. Okay, now in the same type of prism, or in the same prism, okay, suppose acha, in the same prism, so I'm drawing in the same prism, okay, without any different prism. In the same prism, a red light goes somewhat like this. Okay, this is the red. Now what is red? Red is nothing but the white, or this white light is supposed to pass through this, so the deviation of the red light is nothing but this angle, or deviation angle of red light. Okay, and how is deviation angle of red light given? D red is equals to prism angle into refractive index of red minus 1. Okay, so we have two different angles of deviation for red light and for violet light, and violet light deviates more than red light. This much is understood. Now dispersive power is nothing but dispersive power dispersive power is nothing but d theta. Okay, or dispersion. What is the dispersion or angle of dispersion? So angle of dispersion is nothing but angle of dispersion. Angle of dispersion is represented by d theta. It is nothing but deviation of violet minus deviation of red is called angle of dispersion. That means this angle, deviation of violet or deviation of violet minus deviation of red, that means this small angle, okay, is called angle of dispersion, okay, divided by angle of deviation. Angle of dispersion divided by angle of deviation. Now what is the angle of deviation, or what is this theta? I know that violet color deviates some more, red colors deviates the least, but what is the deviation of white light, or how do I find out the deviation of white light? Deviation of white light is nothing but the average deviation of all the light, or theta is nothing but the average deviation of all the light rays. See, average deviation would be given in the question by refractive index of the slab, okay, or for average deviation you can also use the wavelength or the light yellow, okay, because the wavelength of light or yellow light behaves as the average of all the visible rays of light: violet, indigo, blue, green, yellow, orange and red. So this yellow light or the deviation of yellow light or deviation of yellow light is equals to deviation or average deviation, okay, is equals to mu of yellow, sorry, is equals to prism angle into mu of yellow, refractive of yellow minus 1, which is also equals to prism angle into refractive index average minus 1, okay, which is equals to theta, okay. So our dispersive power of a medium is nothing but deviation of violet minus deviation of red by average deviation, by average deviation. And how do we find out average deviation? Average deviation is nothing but the deviation of yellow color or yellow light ray, okay. Now see, in order to simplify this equation, suppose now see, in order to simplify this equation, or can I say dispersive power is equals to deviation of violet. What is deviation of violet? A into refractive index of violet minus 1 minus deviation of red. And what is deviation of red? A into deviation of red minus 1 divided by prism angle into refractive index of yellow or refractive average refractive index minus 1, whatever is given in the question. Out here, if you take a common and cancel it out, it would get cancelled. Or dispersive power is nothing but refractive index of violet minus refractive index of red. This minus 1 and this plus 1 gets cancelled, divided by average refractive index of the prism material minus 1. So this is our formula for dispersive power of a prism. All of you understood this one? Now in the next slide, what you are concerned is about the combination of prism. Combination of thin prism. Thin prism. That means in this slide or in this note or in this chapter or in this section, we study how thin prisms are combined. Okay. Suppose I am combining prism A. Okay. This is prism A of prism angle A, and this is prism B. Prism B and prism A both are thin prism, but prism B has a different refractive index than prism A. Okay. Then the total deviation in this case, total deviation due to both the prism would be deviation of A minus deviation of B. Okay. Suppose the prism are kept in upright position. Okay, thin prism. Prism A, prism B. Then the total deviation. See, suppose a ray of light goes out here. total deviation in this case would be dA plus dB, or deviation due to prism A plus deviation due to prism B. See, the point I'm making out here is, if prisms are kept inverted with respect to each other, the deviation is subtracted. If the prism are kept upright to each other, the deviations are added. Okay, suppose one more third prism is out here. Suppose A, this is prism A, this is prism B, and again third prism is out there, prism C. The total deviation due to all this prism, D total, would be equals to deviation due to prism A minus deviation due to prism B. Why minus? Because prism B is inverted, plus deviation of prism C. That means all the prisms that are upright are added, all the prisms that are inverted are subtracted. Similarly, the dispersion total. What is total dispersion? Total dispersion is nothing but, if white rays of light were there, the ray of light would get separated into 7 continuous colors, and diffraction is nothing but the angle between. Suppose a ray of light got separated into 7 different colors. Okay, dispersion is the nothing but the angle between red light and violet light. So total dispersion total out here is equals to dispersion due to A minus of dispersion due to B out here. In the second case, dispersion total is equals to dispersion of A plus of dispersion of B. In the third case, dispersion total, or total dispersion, or total angle between red light and violet light, is nothing but dispersion due to A minus of dispersion due to B plus of dispersion due to C. All of you understood this one? So the main concept I'm making is, if the prism are kept inverted to each other, the inverted, or the dispersion and deviation of the inverted prism gets subtracted. Okay, and if the prisms are kept upright, okay, the dispersion and the deviation and dispersion of the prism gets added. Okay, so upright prisms, dispersion and deviation gets subtracted, and inverted prism, dispersion and deviation gets subtracted, upright prism, dispersion and deviation gets added. Okay, now what we're going to study is, in the previous slide we saw a combination of prism, or combination of thin prism. So I am to combine two thin prism in such a way, okay, prism number A and prism number B, okay, in such a way so that when a ray of light passes through this prism, okay, passes through this prism, the ray of light, okay, disperses out here, then continues out here, then again recombines out here. That means this is white light, the emergent ray from the prism also is white light. So out here, what is the dispersion? Dispersion means the angle between red light and violet light. So for this combination out here, can I say dispersion for the combination of prism, is zero. Okay, and this kind of topic are studied in deviation without dispersion. That means achromatic combination of prism, or achromatic combination of prism. Okay, out here. Achromatic means out here the white light will get deviated. Okay, there will be angle between, or there will be some angle between incident ray of white light and final ray of white light. But the dispersion of this medium and the dispersion of this medium cancels out each other. Okay, and that kind of combination is called achromatic combination of prism. So for total dispersion to be zero, total dispersion to be zero, okay, dispersion of A minus of dispersion of B is equals to 0, or dispersion of A is equals to dispersion of B. And what is dispersion of A? Nothing but mu V minus mu R. A into mu V minus mu R. Okay, suppose the prism angle of B is B, or prism angle of prism B is B. So dispersion of B is nothing but B into mu V minus mu R. Okay, how is this dispersion? See, suppose this was, okay, okay, this is violet, this is red. Dispersion is nothing but this angle, and this angle is nothing but deviation of violet minus deviation of red. So deviation of violet minus deviation of red, or A into mu of violet minus 1 minus of A into mu of red minus 1. And when you solve this, this is nothing but A into mu of violet minus mu of red, or refractive index of violet minus refractive index of red. Okay, okay, so out here can I say angle of prism A should be angle of prism B? Okay, instead of making angle of prism A is equals to angle of prism B, I have made one more critical mistake out here. Okay, in this formula, if prism A is made up of different material, or U dash, okay, A dash, and prism B is made up of different material, that means this UV and this UV would be different. So let's name this UV dash and this UV, and even this refractive index of red and this refractive index of red would be different. So let's name this UR dash and this is UR. So A into refractive index of violet in prism A minus refractive index of red in prism A is equals to B into a prism angle of B into refractive index of violet in prism B minus refractive index of violet red in prism B. Okay, for the same type of prism, mu V is equals to mu R, or there are no dispersion. Now in this case, what we want to study is the total deviation. Okay, so if this is the condition satisfied, for refractive index A, B and refractive index of the second prism material, then what happens is no dispersion takes place. That means incident white light, emergent is also white light. No dispersion takes place. I incident and emergent both are white rays of light. Incident ray and emergent ray are both white rays or polychromatic ray of light. White ray of light. Now suppose in the same case I am to study what is the deviation, what is the total deviation, or d total, or total deviation due to both the prism. D total is equals to deviation due to prism A minus deviation due to prism B. And what is deviation due to prism A? Mu average, or prism angle into mu of average or mu of yellow minus 1, or mu of average of prism A minus 1, minus of A, or sorry, not A, B, prism angle B, minus of B into average refractive index of prism B minus 1. Out here, remember, the total deviation is not equals to 0. Okay. Okay. So these two formulas or these two relation, if you want to remember, it's well and good. If you want to just see it, it's well and good. So just note it down. Okay. Now the second type of combination you want to try to do is the same prism. Okay. The first prism is upright, or prism A is upright, and prism B is inverted. Now out here, a incident ray of white light gets separated. Okay, gets separated out here. Gets separated out here. Okay, but instead of exiting as a white light, it exists as different sets of light. So out here, dispersion is occurring, but what happens in this special cases, what is happening is deviation of the incident ray and the yellow ray is 0. Okay, so the angle of deviation between the incident ray and the emergent of yellow ray, or the average emergent angle, is 0. So the total deviation out here is equals to 0. D total, or total deviation in this case, is equals to 0, or the incident ray makes the same angle as emergent yellow ray. Okay, and this case is called dispersion. Dispersion without deviation. Okay, or chromatic combination of prism. See the chromatic combination of prism. Okay, in this case, if total deviation is 0, that means in this case, okay, if the total deviation is 0, okay, that means deviation of prism A minus deviation of prism B is equals to 0, or deviation of prism A is equals to deviation of prism B, or prism angle of A into average refractive index of prism material A, or refractive index of yellow light of prism material A. Okay, let this represented by y dash minus 1 is equals to refractive index, or sorry, prism angle of B is equals to prism angle of B into average refractive index of prism B minus 1. Okay, but out here, okay, if this is the case, then there is no deviation. There is no deviation from the prism combination. But out here, what happens is the total dispersion is not equals to 0. So total dispersion total is equals to dispersion due to prism A minus dispersion due to prism B. Okay, or dispersion total is equals to, what is dispersion due to prism A? A into refractive index of violet in prism material A into refractive index of red in prism material A minus prism angle B into refractive index of violet minus refractive index of red. Okay, Acha. Hmm. A beam of light consisting of red, green and blue colors is incident on a right angle prism. The refractive index of the material of the prism for the above red, green and blue wavelengths are 1.39, 1.44 and 1.47. Okay, That means what is happening out here? Refractive index of this one is for red color, green color, and blue color. Now, what will happen to this light? Acha. So, in order to find out what will happen to this light, let us first find out the critical angle for all this light. So, critical angle for red beam, for one red beam. What is the critical angle for red beam? Okay, can I say refractive index of red into sine of critical angle is equals to refractive index of air, which is equals to 1 into sine of 90. Sine of 90 is also equals to 1. Or refractive index of red is nothing but 1.39 into sine theta c is equals to 1. Or sine theta c for red should be 1 divided by 1.39. Okay. Similarly for green beam. For green beam, critical angle should be refractive index of green into sine of theta. Critical angle for green is equals to 1 into 1, which is equals to 1. Refractive index of green is 1.44 and sine of theta c for critical angle is equals to 1. Or sine of theta c of green. What is theta c? Critical angle of green is equals to 1 divided by 1.44. 1 divided by 1.44. 3. Blue beam. Blue beam. Refractive index of blue into sine of is equals to 1. What is the refractive index of blue? 1.47 into sine of critical angle of blue is equals to 1. Or sine of critical angle of blue is equals to 1 divided by 1.47. Okay, now the question is what will happen to this ray that is incident out here. See, all the rays will be incident like this, because in this surface angle of incidence is equals to 0 and angle of refraction will also be equals to 0. The angle of prism is nothing but 45. So if this angle is 45, this angle is also 45, this angle is also 45, and this angle is also 45. So for all the rays, angle of incident would be 45. Angle of incident should be 45. Now this angle of incident should be lesser than the critical angle. Okay, then only the ray would pass through. Okay, so sine c for red is sine of 45 greater than sine of critical angle. How do you understand that? We know that sine of 45 is equals to 1 by root 2 is equals to 1 by 1.44. Okay, now see one thing out there. If 45, suppose sine of 50 is greater than sine of 45, that means 50 is greater than 45. So if sine of theta c is 1.39, sine of 45 is 1.44, which is greater? This is greater. So for out here, critical angle of red or theta c of red is much greater than 45. Understood? See, in a entire 1 by 1.44, if the denominator is greater out here, that means the total value would be lesser. Out here, which one of them has the greater denominator? 44, this one. So this total value is less. So sine of 45 is lesser than sine of critical angle of red. So can I say 45 degrees is lesser than critical angle of red? And if 45 degrees is lesser than critical angle of red, what will happen? The ray would pass through. Okay, with some angle of refraction. Now let's look at the green beam. For the green beam, can I say sine of 45 or 1.44 is equals to sine of, acha, this is equals to 1 point. So for green, the critical angle is exactly equals to angle of incidence. So what would happen? The green ray would graze through the surface of the prism. Okay, this is red, this is green. Let's check for the blue ray. The blue ray critical angle for blue ray is 1.47. Okay, or sine theta c is equals to 1.47, which is lesser than sine 45. So out here critical angle is out here much lesser than 45. So out here 45, this 45 would suffer a total internal reflection. So out here blue ray would suffer a total internal reflection. This blue ray would suffer a total internal reflection. Blue. Now let's check out the option. The separate the blue colors apart from the red and green colors. The blue colors is little bit totally internally reflected. Separate all the three colors from one another. Yes. Not separate all the three colors. No. Option number C is not correct. Separate the red color from the green and blue color. Acha, all the colors are separated from each other, no? Okay. Separate the blue color from the red and green color. Okay, blue color. Separate all the colors from one another. Yes, of course, all the colors will be separated from one another out here. Option number B. Let's look at the question. Okay. A beam of light composed of red and green rays is incident obliquely at a point on the face of a rectangular slab. So out here a rectangular slab is there. Okay. So this is a mixture of red and green light. And both will have different refractive index. Why? Because this is polychromatic light of different wavelength when they're coming out of light. So out here a red will be lesser deviated than green, no? So green will be this one, red will be more or less this one. This is red. And while coming out of the prism, they would come out like this. Now see, while studying prism, we always said that the outgoing ray is always parallel to the incident ray, irrespective of the medium or irrespective of the thickness of the uh, slab and the refractive index of the medium. So there will be two different points and the rays will be parallel to each other. Okay, so let's see. 2 points propagating in two different non-parallel direction. 2 points propagating in two different parallel direction. So it is option number 2. Let's look at this question. Rainbow is formed by reflection and diffraction. Not reflection and diffraction, it is done by dispersion. That means separation of sunlight into its multiple constituent colors, or separation of sunlight into its, so dispersion and total internal reflection. Okay, the only option that has dispersion is option number C. Dispersion is the process of separating a polychromatic light into its constituent rays, or into its constituent colors of different wavelength. Let's do this question. A beam of monochromatic light is refracted from vacuum into a medium of refractive index 1.5. The wavelength of the refracted light will be. Acha, what did I say? Suppose from medium 1, or suppose from air or vacuum, the ray of light goes into water of refractive index 1.5. Okay, that is equals to 1. What is happening out here? Why is the light changing direction? Because out here velocity is reduced, or velocity of light in water is lesser than velocity of light in air. Okay, and we know that frequency into wavelength is equals to velocity, and frequency of the light remains same irrespective of the medium. So if velocity decreases, what happens? Wavelength also decreases. So wavelength will be smaller.